it's nothing more than taking like one variable at a time and expanding it to a multiplexing expression. Like you can take this whole thing and just take A, for example, and the partition all those terms that involves A, like this guy and this guy. No, not this guy. Yeah, that's the only one actually. A, B bar, and A bar with the rest of the stuff. So you got A group, and then you got A bar group, and then all you need is two transmission gates, which is multiplexer, to select between, in this case, for instance, B bar, or rest of it. Now, rest of it, hopefully you'll have a minimized, and when you minimize it, maybe it will become another Shannon's expansion, and so on and so forth. And you keep on actually playing with these multiplexers. Keep on expanding out so that you'll cover everything in that expression using just nothing but a bunch of multiplexers, okay? Just please pause or stop. Just say stop if you want to ask questions, okay? Otherwise, I'm going to fly through it so I can cover some other stuff that you guys might have brought in. All right, largest gain transistor, largest R transistor, this sort of thing. Do we need to review these guys out? I think we're good at this point.
Can you review this?
Yeah, sure. You're going to do R or gain? It's kind of like opposite, right?
Okay.
If you know how to do one, you should be able to do the other one. Gain is indirect, inversely proportional to resistance, opposite, okay? So if you find something that's largest over here, that's going to be smallest over here, and vice versa.
I wouldn't get that.
Okay, so now let's do the gain. Let's do the gain. You have higher gain if your transistor is wider. Okay, so you have NMOS 3x3, and that's kind of like exactly 1x1 transistor. That's just simply a case of having an R. Okay. And this is a transistor that is twice as long as it is wide. That's going to give you 2R. Okay. I mean, if you want me to draw this, guys, there you go. It looks like a square. This transistor looks like a square. And this one looks like actually two squares. Okay, and this is W. Of course, this length. Okay, and this guy looked like two squares but sitting sideways. Oops. Well, that's not proportionally good looking, but you get it, right? So resistance on this is going to be basically half an R. Okay, we're looking for gain, but I'm working on resistance problem, by the way. Okay. So what is resistance for this? PMOS always has twice the resistance. Do you agree? Yeah?
Yeah.
Okay. So what is 6/2? Let's see. What is the resistance of something that is 6 wide by 2 in length? Okay, the same as 3x1, same as 3x, right? 3x and PMOS is equivalent to what in terms of resistance, or in terms of actually NMOS gate is equivalent to 1.5x, which is odd number, but whatever, 1.5x, correct? If you want to put it in a fraction, that's fine too. For and it's equivalent. But what is the fractional for this? Is it what? Help me. 3/2. 3/2x. So what is the resistance of something that looks like this? You tell me. 2/3R. Does it sound about right? Did you guys follow this?
Wait, Professor, could you explain Sorry, I didn't follow. Could you explain how you got the 2 by
So
3?
what I did was actually, I'm taking this guy, right? Which looked like this, right? And I'm just pointing out, hey, that same is actually 3x. Because it's like 3 by 1. 6 by 2 transistor is equivalent to 3 by 1. Because what matters is the proportion. Okay? Proportional is 3 by 1. And I want to question, what is that equivalent to in terms of resistance if we are looking at an NMOS transistor? It's equivalent to 1.5xn, and the reason is because PMOS has lower gain or lower mobility, right? We talked about this many times, right? It's exactly twice as worse, or NMOS is twice as better. So you can do the conducting job that PMOS would do with a transistor that is as large as 3 by x using NMOS transistor that is only 1.5, which is exactly half width compared to this guy, okay? Now, what is the resistance for 1.5N? NMOS that is sized at 1.5, or 1.5 is the same as 3/2, right? Well, that is just, you just flip it around and your resistance is going to be 2/3, 2/3. I mean, that's how you calculate resistance of a transistor when you're given width over L, okay? So it turns out to be 2/3R for this guy,
So to find the
Okay.
resistance for a PMOS, you take the width and you divide it by the length, right, to get the proportion. And then you divide it by 2
Yes.
to get the NMOS equivalent. And then once you have that, you
Yes.
put it in fraction and flip it.
Yes, absolutely. That's all
Thank
we need
you.
to do. Yeah. Did you guys hear that? That 2, 3 of what you pointed out, that's all you need to do. Exactly. Okay. So let's do the same over 12/5. Oh, what a weird number. 12/5. So I'm going to turn it into an NMOS equivalent. Okay. It'll be 6/5. Okay. And then resistance will be what? Somebody want to help me out with this? 5/6R. Does this sound about right?
Yeah.
Yeah. Now let's get to that last question, or actually the original question. Okay. Which one has the largest gain? R, 2R, half an R, 5/6R, 2/3R. Which one of those 5 has the largest gain? Whichever one that has the lowest resistance. Okay. You guys all get it? Which one has the lowest resistance? So this transistor has highest gain. Any questions on this problem?
I'm sorry, could you go over how to do the PMOS again? I feel like something's not clicking for me. You could just go over it one more time. Thank you.
Okay. First, you just find a proportion. Proportion for this guy is 6/3. I mean 6/2. 6/2. Okay. And I'm interested in finding R. And gain is just directly inversely proportional to R. So I just want to find R for everybody. So with that, I will be able to find R easily if I can find equivalent NMOS transistor geometry. So what I'm going to do is take this proportion, and I'm going to actually take half of it. And it turns out to be 3/2. That's equivalent NMOS geometry. That's going to provide same R. And R for that guy is just simply 2/3.
Correct me if I'm wrong, but I feel like in simpler terms, like if it's gain, we're just looking for resistance overall, right? So like if we're doing, it's just always, can we just always think of it as length over width? And if it's PMOS, multiply by 2. And if it's NMOS, don't multiply by anything, right? You just take
Yeah.
the ratio you have,
The
right?
PMOS, well, in terms of, okay, so if there's a comparison problem like this, okay, and I would just, this is what I do. I'll tell you what I do, okay? Let me clean it all up. Okay? This is what I do. I'm just gonna, I don't want to compare PMOS and NMOS because it's just all confusing. I'm just gonna put N here, please. But when I do that, I'm just going to reduce the width by half for everybody. This becomes 3 instead of 6. This becomes 6. And then I'm going to come up with a comparison. Okay, so I'm comparing all the NMOSes with the given geometries. And you know that gain, or if you want to go with the resistance first, resistance is L over 3. I'm sorry, not 3. L over W. Okay, and then gain is actually W over L. Okay, gain. Okay. Is it clear? Is it simpler to do now?
Yeah, I was just saying, like, I guess technically you don't really have to calculate the gain because you just, if it's asking for gain, you're just looking for lowest resistance, right?
Exactly.
Like you said. So
Yeah.
okay.
Yeah.
I don't know. I guess the previous demonstrations or what people were saying in the chat seemed to, I guess, a little more complicated than I was just thinking what it was, just length over width.
We're doing this step at a time, okay? But the big picture is this, what I just showed you right here. I mean, I would take all these PMOSes and turn them into NMOS equivalent, okay? And then resistance is just L over W. Gain is W over L. And you can do the similar sort of thing with the next problem, or any one of these problems that has similar sort of thing. Okay? All right, I think we're good on this. So we'll go to, I want you to remember this. I want you to remember diffusion capacitance of a drain node is proportional to width of the transistor, and everything else, some of them are actually still valid, but not in our book, not for this class. In reality, the story is slightly different, but for this class, capacitance of the drain node is just nothing but the transistor width, okay? I'm sorry? There was a question then. Didn't hear.
So, Professor, if it's proportional to transistor width, then does that not mean it's also proportional to transistor area?
Not really. Transistor area is width multiplied by length, right? We don't really care about the length of the transistor. And you know that from transistor, okay? And here's your diffusion. Here on this side, and there's one on this side. I like to draw these diffusions so that they kind of look like bathtubs, right? This is a transistor. This is width, and this is length. Length doesn't matter. Width determines how tall this bathtub is. Okay, and your capacitance, the capacitance that surrounds this guy, is proportional to the length. And like I said, this is just for this book and this class. Because I know a lot of you guys will question. Capacitance is actually, capacitance for diffusion is area surrounding these bathtubs. And if you just make the bathtub longer, it's not really exactly proportional to the width. How does that work? Well, it doesn't exactly, but I'm not going to confuse you with the reality. Okay, let's skip to the ideal world of this book. Okay, and we're just going to say it's proportional to the width of the transistor only. All right. This kind of problems. I don't think we need to do it, but if anybody wants to see how it is done, maybe I can do some couple of them.
Yeah, could you maybe just run through like maybe one or two?
Yeah, let's, okay, I'll do like this one. How do you size transistors on this NMOS? Well, you could do three here, three here, three here. Right? That's one way. That's actually maybe correct. Okay. It is correct. But then how are you going to size rest of these guys? You know, what it means is that you're going to end up with 1/3 of an R for each one of these things, 1/3 of an R. Okay. And this has to be 2/3 of an R because every path has to add up to 1 R. Okay. How are you going to come up with 2/3 R for 3 transistors in series? You're going to come up with some large transistors. And that's not going to fly. Okay. Over here, 9 over here, for example. It is 1/9. It's 1/9 plus 1/9 plus 1/9, which is 3/9. That's not 2/3. That's like wrong. Okay. So only answer that you can get, actually the correct answer that you can get for this problem is if you sized it, size these guys, just simply by pointing out, hey, look, when you look at this whole network, there's 2 things like this one, 1, 2, 2 things connected in series. And I want like half an R here and half an R here. So we're going to assign 2x here. And then these guys have to add up to, I'm sorry? Question?
Sorry, so no question. No question.
Okay. You want to have a quarter R here and quarter R here, so it's going to be 4x, 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 4x. And then you can get away with 6 on these guys. Because 1/6, 1/6, 1/6, they will all add up to, aha, nice round half an hour. Okay, so this is the correct answer for that problem. All right, and then you know you do the similar for PMOS, except you have to make sure you size each one of these guys twice as wide for ideal circuit compared to the NMOS, right?
Professor, is it wrong to assume that PMOS will always just be the double of NMOS?
That is correct, actually.
Okay,
It's always correct.
thank you.
In terms of ideal sizing, okay? But don't quote me on that when you get a job and work in real world. Okay? That is slightly different.
Great.
For the technologies assumed in this book, that is always correct. All right, so there's the capacitance numbers. Do we need to review capacitance calculations?
Professor, can you go back to 9 so I can see what you said the right answer was?
Number 9, right answer was this, 24446.
Okay, thanks.
Okay, I think at this point I want to pause and actually point out the importance of learning the material as opposed to trying to figure out like how the answers, okay, or memorizing answers. Or, I don't know why. Okay, so I want to point out actually, since there are a lot of you guys already here, there has been a number of complaints. Actually, before I get to that, I want to point out, if you guys have any questions, I'd really appreciate it if you'll just come to me and ask me, okay? If you're unable to find me, just email. Or I mean, this is a nice time point to ask me anything and everything. Because there's so many people who went to, looks like, department and complain that we're getting closed book. The reason why I'm having closed book exam, 2 things. I don't want you to waste all your time flipping through the slides and books, trying to learn how to do a problem or trying to find the answers from that. That is just not gonna work so well, okay? And if you didn't get a good grade on the first exam, that may have been one of the reasons. Instead of learning how to do these problems, okay? Another reason why I don't want to do this open book, open anything exam is because there are lots of sophisticated sharing programs where you can actually have an online discussion with your friends as you do exam, okay? So those are the two reasons, okay? So if you want to go to the department and complain that, hey, look, I'm not giving you an open book exam on the final, I would say I am going to provide whatever information that you need to memorize if you have to memorize anything. All the equations, all this detail, whatever, I will provide either on the exam or I will provide those during the exam if you just ask, okay? That way you don't have to rely on flipping through a bunch of slides to find what you're looking for, okay? So I hope that setting will help you instead of hurt you, okay? I'm not here to hurt your exam performance somehow. I'm trying to do exactly opposite. So if you don't agree with me, let's modify, let's change it. But for now, the exam is going to be closed book, close friends, close anything and everything, except even during the exam. I'm going to keep that chatting window open, and if you have any questions on like something that you could have remembered, but it's not on the exam, I will answer. If you want me to write down an expression, equation, whatever, I will let you know. Okay? Just don't ask me like questions like, is this correct answer? That's not a legitimate question during the exam. I will just ignore your questions like that. But other than that, everything is you know, everything's good. Okay, is that clear to everybody?
Yes, sir.
Yes, would it be possible for you to share with us the formula sheet that you'll be giving us? Because I understand like everything we need, but then
I'm not giving you a formula sheet. Well, first of all, in my opinion, because we don't really need formulas. Okay. Second, if we need any kind of formula, I will leave it on an exam, put it on an exam. Okay. But if you want to learn, I mean, if you ask me for formulas, like for example, Elmer's model, okay, there's a formula, right? Formula goes like this: RC plus RC plus RC plus dot dot dot. Okay, I think you should know that. Okay, that's not a whole lot to memorize.
I know it's meant like you said you were going to give us a bunch of information that we need. I was wondering if you were going to share that information with us beforehand, so we know what's there for us.
Oh, I don't have that. What I meant was, as I type out, as I make up your exam questions, I'm going to embed in these questions in a way so that all the information that you need is there for you to answer without looking up any slides. And if you still have problem remembering things that is not clear by just reading the exam questions, then I will provide that for you on the chat window. Is that okay?
Professor, would that include something like the layout of a certain type of adder, or not the layout, but the schematic of an adder if we need to like analyze the delay or something?
I didn't follow your question.
So, in some of the delay questions, when we're, calculating the delay or using the delay of like a ripple adder or a carry adder, sometimes we're given the delay of the ripple or carry, but sometimes would we have to be able to calculate that ourselves? And if that's the case, would we be told the fundamental parts of those adders?
if you want me to show the picture of what's inside of each one of the adders, I could do that, but that's absolutely not necessary for that kind of questions.
Okay, if it's not necessary. then
Yeah, because adder, we're treating it. I mean, when we have a problem that treats each one of those, like for example, the adders as boxes, then they're just simply boxes of unknown design. We don't really care what's inside of it. All we need to know is timing through those boxes, and they will be given to you. Okay. Is it kind of clear?
Yes, that's clear.
For whatever reason, and if you need to know like what adder should look like inside for the exam, then actually if you ask me, I will show you. I will just post it, okay, on the sharing window or otherwise. Okay. If you don't need adder design to do that problem, then I'll just simply state you don't need that. Okay. So if I ask you to, you know, for example, okay, so this voltage on the gate is related to the current during linear. Thank you. Okay, so if I give you a question, for example, in your mode of a transistor is gate voltage related to the current geometrically, exponentially, or linearly, okay? And you just don't remember the linear expression, okay? If you ask me, I will give it to you. I'll give it to you. Okay? But in that problem, if you ask me, can you give me the current equation for saturation mode, linear mode, and cutoff mode? I will not give it to you because you don't need them, right? Is that sort of clear? So in short, what I'm trying to point out is think of me as your open book. Okay? And whatever that you have to do on the exam, I will try to incorporate as much as possible all the information necessary for you to do these problems without opening up the book. Okay? So there, I mean, I think we had more success that way for certain groups. So I'm just trying to propose that this is probably a better option for you, for us all. Okay. All right, now let me go back to this exam and see if we can just finish talking about it, because this circuit goes on and on and on, right? We learn how to calculate capacitance, and then we get to actually a layout. Before we get to the layout, you guys have any questions on like how to find capacitance, how to find RC of the circuit, how to find R of a node, this sort of thing? Are we good? All right, let's go to the layout then. Oh, how do you figure out what this layout is? This is actually a problem stems from your labs, okay? And when you look at a layout, I want you to be able to trace your connection and realize, oh, there's a transistor right there, and there's a transistor right there connecting to ultimately this metal, which is output. See, it's indicated as an output. Okay, so your output is getting connected to the ground through two transistors in series. And then I'm going to take my output and see what happens on the other side. Oh, it is also getting connected to actually two more transistors on the other side, again in series to the ground. There you go. With that information, can you come up with an expression for your output? And answer should be yeah. You're going down to the ground, so I'm going to put bar over the whole thing, and I'm going to state it is really nothing more than A ended with a B, or B ended with the, oh, I'm sorry, C ended with a D, that gets me down to the ground. And if you look at it carefully, okay, one of these answers is correct. Oops. Oh, well, sorry. One of those answers is correct. Use your algebra again to find, to figure out which one's correct. Okay. So there you go. I am going to give you another layout, kind of like this, maybe even easier, and ask you to figure out what the expression should be. Okay. And in fact, I might even give you like this problem. Let me try to see if I can scroll it here. Like this problem.
Professor,
Yeah, go ahead.
do you mind going back to the question again?
This one?
Yeah, I thought like the fourth transistor in series, shouldn't they be like A, B, C, D instead of A, B, or C, D?
Look at the connections. This is ground, right? Your ground is connecting here. Just look, and then this is your output. Your output is going through or getting connected to the ground. How? In terms of transistors. 2 transistors in series over here. Okay. And 2 of them on the other side, also in series. So as long as this path is connecting or this path is connecting, you'll have a connection down to the ground. And that's the point.
I get it. Thank you.
Okay? So it's A, B, or C, D. That expression gets you down to the ground. Therefore, I'm going to put bar over the whole thing to indicate that that's going to give me a 0 when this is true. Okay? And which one is which one of these expressions is same as this guy? I'm not going to answer that. That's your 248. And if you still don't see it, no comments. All right. let's.
Professor, I have a quick question about that layout.
Which one?
Yeah, that one. So how do you know that it's with the bar? That's what confuses me.
This bar?
Yeah.
If this expression is true, logically think about it. If this is true, if A is true and B is true, what is happening to your output node? Well, you tell me. What is happening with your output node? What's going to happen to your output node if A is true and B is true? Or C is true and D is true?
It gets connected to ground.
Exactly. So you get a 0 on the output, correct? So having 1 here will give you a 0, give you a ground. So I want to complement the thing out to give you that expression you're wanting. Okay? I want you to review out that second lecture we had.